Hi students, now we are going to discuss about the Wheatstone's bridge, which is an important application of Kirchhoff's laws. We have studied Kirchhoff's first rule and Kirchhoff's second rule. Both are being applied in the construction of the Wheatstone's bridge. This is also called as Wheatstone's network. You can look at the circuit. This only is called as the Wheatstone's bridge. It consists of 4 arms: AB, BC, CD and AD. So 4 resistors respectively P, Q, R and S are connected across the 4 arms. Now between the points B and D, a moving coil galvanometer whose resistance of the coil is capital G ohm is connected. So this may be considered as the 5th resistance of the circuit. Already 4 resistors are on the 4 arms. Okay, they are P, Q, R and S. In addition to that, this resistance of the galvanometer G is connected between the points B and D. Now the junction A and the junction C are connected across a battery of EMF E. So the positive terminal of the battery sends the conventional current. So this conventional current I ampere, after reaching the junction A, it is divided in the 2 branches. So through the branch AB, the fraction of the current flowing is I1 ampere, and through the branch AD, the fraction of the current flowing is I2 ampere. Then again at the junction B, this current I1 ampere is dividing into 2 branches. So out of that, I3 ampere is flowing along the path BC and Ig ampere is flowing from the point B to the point D. Then in the branch D to C, the current flowing is I4 ampere. So the current I3 ampere and I4 ampere will meet at the junction C, and once again it will be joining as the main current I. So here these currents in the various branches are shown in the circuit like this, and particularly we have assumed that the current from the point B to D flowing is Ig. That means I have considered the point B is at a higher potential than the potential at the point D. Then only the current can flow from the point B to D in the downward direction. Okay. Now what is the use of this Wheatstone's bridge? It is an application of Kirchhoff's law. Okay. What for we are constructing this means using this Wheatstone's bridge, we can compare 2 resistances. The ratio of the resistances can be found, or by using a known resistance, the value of the unknown resistance can be determined. Very helpful to us. So now first we are going to apply Kirchhoff's both the rules. Now look at the junction A, all of you. Junction A. Then this is junction B, junction C and junction D. At some junctions you see A, the currents are leaving. At junction B, the currents are meeting, some current is leaving. At junction C, some currents are meeting. Like that at junction D, some currents are meeting, some currents are leaving. So first we are going to use Kirchhoff's first rule. So I will consider the 2 junctions B and D. So first Kirchhoff's current law, Kirchhoff's current law, that is first rule. Okay, applied to junction B. Applied to junction B. So at the junction B, the current I1 is flowing towards the junction. Okay, I1 is flowing towards the junction, so it is positive. So I will write I1 as positive. Then the currents I3 and Ig both are leaving the junction B. They are going away from the junction B. Therefore I3 and Ig are negative. So minus Ig minus I3. So the algebraic sum of the currents meeting at the junction is equal to 0. That is the Kirchhoff's first rule. So I will rewrite this equation. I1 is now equal to Ig plus I3. Okay, this is the equation 1. Similarly, I am going to apply Kirchhoff's current law. to the junction D. So Kirchhoff's current law applied to the junction D. So for the junction D, which are the currents entering the junction? I2 is entering, Ig is entering. So these two currents I2 and Ig must be positive. So I2 plus Ig, and that must be equal to the current I4 which is leaving the junction. So this must be equal to I4. So I2 plus Ig minus I4 must be equal to 0. I can rewrite this equation as minus I4 equal to 0, or otherwise I can shift the I4 term to the right side first itself. So I2 plus Ig is also equal to I4. Both are one and the same. So this is equation 2. Next, in this closed loop, okay, in this network, now there are so many closed loops. Say for example A, B, D, A. Then B, C, D, B. These are the triangular loops. Then A, B, C, D, A. This is a square loop. Then A, B, C. Then through the cell E up to A. Then A, D, C, E, A. Like that, there are so many closed loops or branches in this entire network. Now I am going to consider only two closed loops. So I am going to apply Kirchhoff's voltage law. So for any two loops, so Kirchhoff's voltage law is to be applied. So for that I am going to consider first a smaller loop A, B, D, A. So KVL applied to the closed loop, okay, applied to the closed loop A, B, D, A. So you can see here A, B, D, A. Now according to Kirchhoff's voltage law, the algebraic sum of the current and the resistance through each and every branch of the loop must be equal to the algebraic sum of the EMFs. Now in this branch A, B, C, D, you see here A, B, B, D and then D, A. So I first proceed from A to B. I am proceeding from A to B. The current I1 also is proceeding from A to B. Is it not? Therefore the IR product must be positive. So the current into resistance is I1 into P. This is positive because I am proceeding along the direction of the current. Then I am proceeding from B to D in the downward direction. The current Ig also is flowing in the same downward direction. So this Ig into resistance G product is also positive. So this is plus Ig into capital G is also positive. To close the loop, I should proceed from D to A. I am proceeding from D to A. But in which direction does the current I2 is flowing? It is from A to D, opposite to the direction of proceeding. Is it not? Therefore, this product I2 into R is negative. So this is minus I2 into R is equal to 0. Okay. So as usual, the negative term is shifted to the other side. So the same equation can be rewritten as I1 into P plus Ig into capital G is equal to I2 into R, and this is the equation number 3. Okay. Now once again another loop I am going to consider, that is A, B, C, D, A. So Kirchhoff's voltage law applied to the closed path A, B, C, D, A. So in this closed path, if I apply means I proceed from A to B. Okay. So I proceed from A to B. Current I1 also is in the same direction. Therefore the product current into resistance product I1 into P is positive. Then I proceed from B to C. Current I3 also is flowing from B to C. Therefore the IR product, namely I3 into Q, is also positive. Okay. Now I have to proceed from C to D. But the current I4 is proceeding from D to C, opposite. Therefore the IR product I4 into S must be negative. So this is minus I4 into S, negative. Once again I proceed from D to A. But the current I2 is flowing from A to D. It is against the path of proceeding. Therefore, that also is negative. So, minus I2 into R. Okay, minus I2 into R. So the algebraic sum of this product of current into resistance I have written, that is equal to 0. Therefore, why it is 0? Because there is no battery in this loop. Okay, there is no battery. Therefore, this IR product, no, we are taking it as 0. There is no EMF. Okay, now I1P plus I3Q is now equal to, this is taken to the other side, no? Therefore, this is I2R plus I4 into S. So, this is now equation number 4. Okay? So, these are the 4 equations we have derived by applying Kirchhoff's first law and Kirchhoff's second law. Okay. Now, in this picture, I have drawn such that the current is flowing from the point B to the D of the loop. That means which point should be at a higher potential? B is at a higher potential and C is at a lower potential. Suppose if B and D both are at the same potential, when the potential at B and D are equal, can there be any current flow in that branch? No. That condition I am going to assume. Okay. So, if potential, okay, if potential at B is equal to potential at D, okay, potential at D, then the current flowing through this branch Ig must be equal to 0. This is very, very important condition. When the current through the galvanometer is equal to 0 means, then only this Wheatstone's bridge is said to be balanced. The bridge is said to be balanced. Okay. So, when no current flows through the galvanometer, the pointer of the galvanometer will read the center 0. Okay, it will read 0. So, this is called as null deflection of the galvanometer. So, when the galvanometer shows null deflection, 0 current, then the bridge is said to be balanced. Therefore, I am going to substitute Ig is equal to 0, okay, in all the previous equations. So, this is called as what? A null deflection of the galvanometer. For the balance of the bridge, there should be no deflection in the galvanometer. Now, in the first equation, I1 is equal to Ig plus I3. If Ig is equal to 0 means, therefore, I1 is equal to I3. So, this is equation number 5. Similarly, in equation 2 also, if you substitute Ig is equal to 0, then I2 is equal to I4. Okay, so I2 is also equal to I4. So, this is equation number 6. Then in equation 3, okay, Ig is equal to 0. Therefore, I1P is equal to I2R. So, I1 into P is equal to I2 into R. So, this is equation number 7. So, 5, 6, 7 is one set of equations. One set of equations. Okay, students? Now, you look at the equation number 4, which already we have derived. I1P plus I3Q is equal to I2R plus I4S, is it not? But from equations 5 and 6, from equations 5 and 6, I1 is also equal to I3. So, here in place of I3, shall I substitute I1 in this equation? Okay, in place of I3, I can substitute I1. Similarly, in place of I4, I can substitute I2. Okay, I am going to rewrite. Okay, so I will rewrite the equation 4. So, rewriting equation 4 by substituting I1 is equal to I3 and I2 is equal to I4. So that the first term is what? I1P. So this is I1 into P plus I1 into Q. So that is equal to, right hand side is what? I2 into R plus I2 into S plus I2 into S. So in the equation 4, I3 is substituted by I1 and I4 is substituted as I2. So that on the left hand side the common factor is I1, okay, into P plus Q. So on the right hand side common factor is I2 into R plus S. So this is now equation 8. equation 8. Now look at the equation 7 and 8. I am going to divide equation 8 by equation 7. Okay. So dividing equation 7 by or equation 8 I will divide. Okay. 8 by equation 7. On the left hand side of equation 8, we have I1 into P plus Q. On the left hand side of equation 7, no, I1 into P. Now on the right hand side, it is equal to I2 into R plus S divided by I2 into R. Okay, I2 into R. So we can cancel I1 and I1 on the left hand side, I2 and I2 on the right hand side. The remaining is what? P plus Q divided by P. I will write P by P plus Q by P is equal to R by R plus S by R. So that P by P is equal to 1. 1 plus Q by P is equal to R by R is 1 plus S by R. Now this 1 and 1 also can be cancelled. Therefore what? Q by P is equal to S by R. Okay. Therefore Q by P is equal to S by R. Now taking reciprocal. Okay. Taking reciprocal. So we can write P by Q is equal to R by S. So this is the final equation which we are numbering as equation number 9. So P by Q is equal to R by S. So this is the condition. Okay, condition for the bridge balance. So in the examination, derive an expression, derive the condition for, okay, the bridge balance. Means you have to derive that P by Q is equal to R by S. And this is a very important question in the Tamil Nadu State Board exam. And all competitive examination problems are based on this, okay, in this particular chapter, because it is an application of Kirchhoff's law. So P by Q is equal to R by S is the required condition for the balancing of the Wheatstone's bridge. So what is the Wheatstone's bridge or network we have studied? It is an application of Kirchhoff's laws, and it is used to compare two resistances. Also it is used to find out the unknown value of a resistance by comparing with the known value of resistance. The same bridge is in a modified form. You are going to study the next topic. The modified form of Wheatstone's bridge is called as a meter bridge. And meter bridge is also very much important topic for your exams. Okay, fine, see you.